also mentioned about something like well state measurement. So this is another key aspect which these are time sensitive, but these also will help us pass the information over long distances, as we'll see, right? So QNT-SIM has a modular architecture.
Sorry.
Yeah, QNT-SIM has a modular architecture, so there are different layers to it. There's kernel layer, hardware layer.
Read audio. Okay. All good? Thank you. So QNT-SIM, that is our quantum network simulator, our product. That is based on modular architecture. What I will do is I'll directly go to a pictographic representation. So these are the different layers which go behind our network simulator. So there is the application layer, network management, entanglement management, hardware, and there is something like resource management, which is actually trying to transmit information from A to C. But the idea is that A would have, say, some number of memories. A and B would be connected by something like a classical channel. Then there would be a quantum channel. Then similarly for B and C. And as you see, quantum data will decode. So the point is, as you're trying to transmit this from A to B, there will be noise effects on your channels. There will be more attenuation and all. So I'll tell you more about it. So the idea here is that this is a very complicated system. We'll keep breaking it down. But your resource management over there will make sure that there are enough resources to actually carry out the task you are trying to do first. Application one, which is the core from the user perspective, this will make sure that what protocol are you using? Are you using E2E or are you using, say, BB84? There are many quantum communication protocols which would be there. The network management again is one key aspect, which this looks like a network node of topology and also then that would be also taken care. And there are two ways of distributing. There is something which we call as prepare and measure. Communication protocol, and there is entanglement based. So our simulator can do this, but mainly focused on this entanglement based communication. So that's why we need an entanglement management which coordinates with the hardware layer. So this hardware layer, one might think that okay, do we really have the hardware on that? So this hardware layer also is where all our physical components lie, right? Okay. Yeah. So I think I mentioned about these, but I will just go back to yeah. So kernel, there's something like kernel layer also, which is not there in the diagram, but kernel layer works in the background. It's taking care of the quantum state. So we are all interested in quantum computing. So any of these protocols actually have quantum gate operations which take place. So kernel layer will take care of that. Hardware module, as I was saying, will represent all the physical hardware that would be there. There would be memories, detectors, light source, quantum channel, classical channel, and beam splitters, BSM units. Entanglement management layer, as I was talking about. Then there's resource network. Transport layer will make sure that messages are communicating. So in our normal networks, internet right now, we have all this handshake protocols and everything. So transport layer will make sure that there are things happening to make sure that we are sending the information to the right place. Like we are mentioning, if A wants to send to B, it should not happen that it has to check, okay, is B ready to take the information, and then proceed to send the information. So these are the components, right? Yeah, please. Anything? Oh, okay. Yeah. So this is a bit tricky part, but I think I should mention this because we are going to have a demonstration, and we just want to tell you what it means by the input parameters, or what are the input parameters. So the node will have memories. So there will be quantum memories in each node. Then there would be coherence time, which would make sure that how much time before this data that the memory has expires, like in the sense that it decodes completely. So then that is a very critical thing, which we also call expiry time. Then there is efficiency, probability of the quantum memory successfully emitting a photon when excited. So in the sense that we are actually working on photon. So there are many protocols. They work on different concepts. So if you talk about quantum memory which is trying to emit photons. So probability of it being successfully done would be taken care by the efficiency. We want 100% efficiency, but that's not always the case. Yeah. Then there is something like you can do that without disturbing your, actual data that you're exciting to. Like if you're exciting to state 1, you don't want it to decore, but you also want to de-excite it so that you can maybe excite to a plus state later. That is one key important thing. Then there is fidelity. This is something which is very crucial in computing aspect as well. So fidelity is trying to, we talked about entangled states, like say these entangled states, phi plus, psi plus, so all these. So the point is, if there is an entangled state, let's say 0, 0 plus 1, 1. Okay. So what might happen is that actually this is the ideal state that you expect, but because of noise and everything, it might be that this state is not exactly as we expected. Maybe it's something like this. So a fidelity is a measure of how this is your, like you're seeing this state in real, but this is what you expected. So fidelity would be a measure of how close this is to what you expected or ideal case. So some fidelity, I'm not going to the calculation, but says this fidelity is 0.7. So we are saying that this one that we have is fidelity 0.7. Get into that in the entanglement generation part. So yeah. Attenuation. So this I was talking about when you talk about per kilometer. So this is a metric. There is more calculations behind it, but I'm again not going into the exact key message exchanges that happen. So that would be taking place on the classical channel. So what we do is we define or we approximate a classical channel delay as well. So the whole idea here is that this works on a photon based thing, and it works very quickly. So the metric that we talk about here, actually we are working in picoseconds. So our simulator works in picoseconds, which is a remarkable feat in itself. So the idea here is that we cannot afford much latency. So we want to minimize latency as well, which is through the quantum there might be latency, or through the classical there might be delay or latency. Okay, so we use something coming to the like the detector. Yeah. And then, okay, so we'll be discussing something like protocols ahead. So these parameters would be useful there, but I'll just talk about gate fidelity. Gate fidelity is nothing but when we do our quantum operators, we talked about say some gate like X gate. So gate fidelity is this error that actually happens when you're physically trying to do the operation. But again, this is simulator, so we want to keep a simulator, we want to keep as real as possible. So we add such parameters to make sure that we know that yes, we acknowledge that yes, there is error, and we want to put that in our simulator as well. Okay, so then there is source interaction. Okay, again there is mean photon number, light source network. So simulators like ours, QNT-Sim, allow us to adjust these parameters and observe their effect on the quantum network behavior. And we also account for something like classical channel delay, as I was mentioning. We hope that we have memory which are highly efficient, and we have something like atom cavity cooperativity, which makes sure that entanglement generation is of high magnitude, so like high purity. So these are the few things which are crucial for our network performance. And one thing which we have keep talking about in quantum is that it's completely probabilistic. So we talked about something like shots, that you put it on IBM, you do it like 1024 times. So why do you do all that? Because it is probabilistic. So you want to keep repeating and take the measurement, and then see how it did, like how your circuit did or how your network did. So this again is probabilistic. But that said, we want to also take help from it, in the sense that if we are to discuss, and then we will look at a demonstration of our quantum network simulator. So when we talk about application, we talked about protocols, or we talked about like maybe QKD protocols. So those are on the top layer, like application. But the actual working of the network simulator is based on three things, which is entanglement generation. So I'll try to mimic on this. Generation means before you send any information from A to C, you want to generate entanglement. So how you do this is you generate entanglement between A and B. Then you generate entanglement between B and C. Then you do something which we call as a swap. So you then swap. I'll get into more detail, but then you put on, and you might not actually have any connection only. So the idea is that to distribute this information to a long distance, we have nodes in middle which help us, swap and put the information forward. So okay, we use the Barat-Koch protocol here specifically for our, entanglement generation. It is a matter qubit based protocol. Let's see. Okay. So this is how, I was showing these are all quantum nodes. So quantum nodes will have your quantum memories, and there is the BSM node. So I'll do one thing. I'll go through the protocol steps. Again, I've added a lot of details, but it's just for the sake of completeness. What I can do is I can try to just give you an intuition. Then there is a detection window. So when you excite a photon will travel to the BSM node, but at the BSM node, there is a time interval within which you want to detect the photon. That's a success. If not, it's we repeat it. So the success condition is for the first round, detection of exactly one photon. Okay, yeah. So we need to detect exactly one photon. If there is 0 or 2 photon detection events observed, the scheme fails. So this is the round one for the, heralding that we call, and this has double heralding. So first round we want to detect only exactly one photon. Then in the second round, after the relaxation, so a waiting period is implemented to allow the actually matter qubit, in the sense it's a physical qubit cavity. So this we are doing in a simulator, but I'm talking about the protocol only now, like assuming that this is an actual physical protocol. So in that we let the thing de-excite, which is relax. Then after that we apply a X operation. This is just the algorithm. Then there is the second excitation that happens. We again apply pi pulse to each of the qubits and photons so that they reach the BSM node for detection. Again, exactly one photo detection event must be observed, and maximal entanglement. If both rounds are successful, completed, then the state, like something like psi plus, psi minus, which is maximally entangled state, is prepared with unit fidelity. So again, this is ideal, like unit fidelity is ideal case. So robustness. So we do this double heralding to make sure that our protocol is robust against, detector losses and spontaneous emissions of photons and all. So, yep. Okay. So this is where we are talking about atom cavity cooperativity. This is a physical parameter, and the fidelity of the entanglement generated is this complicated equation, which we can just see for once, because I just want to show you that, okay, there are other things like, which affect the fidelity. So there is this bare atoms optical decay rate, there is this optical pure dephasing rate, and there is this difference between optical transition frequency of two atomic memories. So this equation, yeah. So this is how your fidelity varies with C, which is atom cavity cooperativity. So you can see this C actually normal ranges from 50 to 500. So if we have something like 50, we are, probably having a very high fidelity already, but we want to probably reach a fidelity which is as close to 1. So if you see as increasing this, your fidelity is reaching 1, but not exactly 1. It's getting closer there, 0.999. Okay. Yep. One important factor here is that this protocol, if succeed, we'll get the fidelity as the equation, but protocol could not succeed, it could fail. So this is something which our network simulator has to, do in the background. Like it has to keep trying to succeed, or, make sure that this entanglement generation has successfully happened. So the idea here, as I was saying, you will first generate entanglement between A and B. So I'll just write down few steps. Entanglement generation, right? And then you will do that between B and C also. Okay. So one very interesting thing that will come after this. Okay, I'll give this perspective after I discuss the concepts. Okay, so we have entanglement purification. So after you do entanglement generation, we actually have a lot of memories. There could be like say 24 memories in A, similarly in B. So one very good algorithm that we have over here is that we can combine low fidelity entangled states into high fidelity entangled states. So we do that by this protocol, and they are done in pairs. So this is also called the BBP SSW purification protocol, which was given by these extinguished scientists. And so I'll try to get a picture. Yeah. So very famous. We always talk about Alice and Bob. So over here, let's say Bob has these two pairs and Alice has these two pairs. Now they are connected. They are entangled. So they have one qubit here, another qubit with Bob, one with Alice. So the point here is that now this fidelity might be low. It might be like say 0.6, 0.6. So this protocol, purification protocol, allows us to increase the fidelity by combining low fidelity pairs into high fidelity pairs. So you can see over here is just a pictorial representation, but the idea here is that F3 would be greater than max of these two, right? So after we do generation, what we do is that we want to make sure that our fidelity is high. So it's very important the fidelity is high. So for that, what we do here is now entanglement purification. So let us look at that protocol for once. One second. Okay. So it takes two identical copies of noisy entangled states as input. So these are low fidelity qubits. Then it applies some quantum operations. So this quantum operations, when we do it in the kernel layer that I was saying in the quantum network simulator. Then after that, we have to communicate something classically as well for this protocol. So that's why we have something like classical channel. So classical communication between two separated parties is used to coordinate the action and the pairs which. So in this, again, all these protocols are probabilistic. So sometimes it might fail, sometimes it might succeed. So most of the time it succeeds, but when it fails, we don't need those pairs. So we want to free those pairs. So the idea is that we discard them if it fails. If it succeeds, we keep the higher fidelity pair. Okay. So here, just trying to give the picture here. So actually, this node has many memories. This node also has many memories. This node also has many memories, and each of them, they start pairing up. So maybe say A1 pairs up with B1. Similarly, till A24 pairs up with B24. So these are the pairs that we're talking about, right? Yeah. Yeah. So again, this is a complicated equation to just show for the sake of completeness. So this equation is the output fidelity of the new entanglement pair that is created. One key point here is that the two pairs that we're trying to combine, their fidelity is same. So we try to combine pairs with say 0.7, 0.7, and once you work out the math, you will get say 0.78, maybe you will increase a little bit. And one good idea is say like you combine the pairs, you got say 0.78 now, then you have more pairs, right, of 0.78 because you did that protocol. So you can again do multiple purification. So the idea here is that, okay, you generated entanglement between A and B, B and C, and you do entanglement purification. This you can do multiple times. This is to reach say a target fidelity. So now it's a good point to tell about what's the idea about this fidelity, why there is so much calculation. So the idea is that the user or you guys, whoever we are, we want to make sure that the information is transmitted definitely, but also with high fidelity. High fidelity means you're not losing your information as such. So you want to make sure it's as close to 1. So that's why we try to do this multiple times and keep increasing our fidelity of our pairs. Okay, there is this formula and there is also like the success formula. So not every time is successful, but this success rate is still very good compared to swapping success rate. I'll get to that. Okay.
Excuse me, sir.
Please.
Yes, sir.
Yes, please.
F3 is equal to max of F1.
Okay, the figure. Yeah, this is just, yeah, please.
Max.
Yeah, so,
Can we consider this rectangle?
okay, so one thing I'll have to tell that this is just to tell you that F3 is greater than F1, F2 ka, like the actual protocol only requires same fidelity. So the 0.7, 0.7 is F1, F2 here. So what I'm trying to just show in that picture is that your F3, which is the new pair, would be greater than max of these two, first thing. And your doubt, please, again. So, yeah, please. Okay, I'll tell again. So the idea here is actually you're combining these two low fidelity states. Yeah, combining physically. You're combining, not yeah, and then you get a higher fidelity pair.
Why is not purification is wrong?
Okay, purification is a word such that to just okay. So we have water. So we want as pure water, right? But assume we don't have pure water. Assume we have like so this is say 100% pure. We have say 80% pure water. So the just idea is that if you have two jugs of 80% pure water, you mix them, combine them, and using this physical protocol, you expect to get an increase. Let's say you got 90%, like that. So that's the idea, and mathematically, sorry, where's the formula? Oh, this is back. Okay. Yeah. So mathematically, when you plug in these values, you will see that f dash is greater than f. F dash will be greater than f when you put f is greater than f. So the idea is that if you want some 100% pure water, you will at least want to start with 50% pure water, both cases. So your f would be greater than 1/2, and your increased fidelity, your purification is word to just say you're purifying it, like in the sense you're increasing its fidelity. So it's just a intuition giving word, but it doesn't really yeah, that's it. So purification means that. So you want to purify your states, and so these are combining. So you are actually, so let's say we have 4 of them. So when you combine these two, you will get 90% pair, and you can do it again. You can combine these two, and maybe you will get 95%. So 4 to 1. So you're actually combining pairs, and the idea is that's why you will do multiple times. And this is also one reason why we have many memories, because you might lose your memories, you might lose them in your purification stage. Yeah. Okay. Any other doubts? Please keep asking. And these are all like very state-of-the-art concepts right now. But the idea of the FDP should be to also give you an insight into what's happening in the industry. So we are definitely happy to answer your doubts if you have any, please. So this is the success probability which I was saying. Again, it's not of much mathematical concern as of now. That's why I'm not doing the maths, but the idea is important. So that's why I think this should be very helpful. Okay. Okay. So after we do this, I was talking about something like swapping. So swapping is something which will help us extend the entanglement across distances. So, okay, yeah, there is a photo which I have. Okay. Yeah. So in this figure, we can actually just see that B could act like a BSM node, in the sense that A and B first you generated, B and C you generated, then you did purification between A and B, you did purification between B and C. So you're trying to like increase fidelity of your memories, memories in each nodes. But now you want to extend, now you want to connect A and C. You say, okay, yeah, they're connected now. They're connected through B. But no, I mean like a connection which allows this information to, travel 100 kilometers at once. So how do you do that? Actually, you do that by having a network which allows you to do something like BSM node or this swapping protocol at your center node. So now the next step would be entanglement swapping. Okay. So two short distance entanglement pairs are consumed to distribute to long distance entanglement. So this is the idea. Yeah, so swapping helps you extend. So you do purification. Purification is a word which you can keep in mind. Okay, you generate first, purify, you increase the fidelity. Swap is to extend. So you want to extend its, reach. So extension of entanglement. So I'll just write extend. Okay. Sticking together. So technique enables you to stitching together of short entanglement segments to create a long distance thing. So the idea here again is like we're talking about, I was saying that, from Vizag to Vizag Beach. So from GVP, you want to go to Vizag Beach and then Hyderabad. So what probably would happen directly to Hyderabad, if it's not possible, then you probably have a BSM node in between Hyderabad and Vizag. which you might suggest something in midpoint, but I don't know. So the idea is this. So before you communicate a longer distance, you have nodes in middle to help you, distribute this data using our completely quantum processes. Yeah. Yeah. So this swapping is a fundamental for construction of quantum repeaters. So actually, if you look at these are quantum nodes. They will also have something like BSM node in them. Then they will act as repeaters. So B will act as a quantum repeater to, like how we have classical repeaters. Okay. Yeah. So initial setup is A and B pair, B and C, B as BSM node. The joint measurement effectively swaps. So the idea here is actually I'll see if I have more. Okay. So the idea here is when you do the Bell state measurement here, so you transmit information from here as well as here. But when you do Bell state measurement, you swap the information in the BSM node and send it back through the classical channel. So when you do that, actually when you do this, you are extending the entanglement now from initially being A and B and B and C to now A and C. So that is just the core idea over here. Yeah. Yeah, and yes, so this has a success rate of around 0.64. So what that means is that this is again, as we keep advancing this, we hope that our hardwares will support more, or we'll have more advanced swapping protocols. So the idea here is that 64% of the times your swapping will be successful, but 36% of the time it will fail. So right, this is some important parameter which I was talking about before. Okay, so let me do one thing now. Let me go back to some of the parameters and then talk about QNT-SIM perspective, and then we can start looking at the actual network simulator. Right. So I was talking about swap success rate. Then there is something like swap degradation. So again, there are imperfect. We have noise in quantum gates. So these imperfections of quantum gates right now would again be given by something like swap degradation. Okay. Any doubts someone asking? No? Okay. So QNT-SIM perspective. Yes. So our QNT-SIM accurately models the physical component involved in the Barak-Code protocol. So the protocols I mentioned are all physical protocols. They need to be simulated in the simulator. So a simulator will is using Barak-Code protocol for entanglement generation, and yeah. So the simulator traces quantum state, lifetime, fidelity of entanglement as complex arrays throughout the process. So there is a lot of complex computer science actually going on in background to make sure that your states are keeping track of. If you're say this starting before even entanglement generation, your state is something which is raw example. So it's raw, it's not entangled yet. So once you have a raw state here, you entangle them. So you mark it as say entangled state. Now once you have say entangled state, I was talking about purification. So you need to track through all the entangled state and see which states have the same fidelity. So you try to combine them, purify them. After you combine, you lose the initial states. So these are the few things which our simulator actually is great at and keeps track of. Then there is classical control messages. So if you're talking about quantum network or anything quantum that we talk about, is completely takes help from classical systems right now. So there will be classical communication happening to make sure that okay, we send a negotiated message first, then there is measurement results. So BSM or any other node that has once you have photo detection, so you want to send the results back as well. So BSM actually node over here, when it does the swapping, it sends results. So it takes from A and C, then it measures and sends results back. And while sending back, it doesn't send the A's result to A, it sends A's result to C and C's result to A. That is how it does the swapping actually. Yeah. Again, so there might be failure. So if there is a failure, you re-prepare the qubit and you re-attempt. So this is what a simulator is. Okay, so now again to the purification. Yeah. So we use BBP SSW protocol for purification, which I talked about. There can be other protocol as well, but we are using this one right now. And as I said, there is 2 instances of protocol. they determine the, okay, yeah. So I gave you a formula for probability of success. So this also has some probability of success, right? And the simulator then randomly determines success or failure. So this is how we are trying to mimic a simulator. So the idea is that if you are doing a physical process, if you do actual physical process, it may succeed or may not succeed. But in a simulator, we want to mimic it. We want to mimic if that success happens, how it will happen. So for that, we again keep track of some random functions to make sure that we are say a probability is 0.9. So we want our simulator to say succeed 0.9 times and fail 10% times. Right. So again, there are messages exchanged between them, and the iterative resource. We are also making sure our resources are keeping track of using the resource management. And there is something which is end-to-end latency. So you might see when we see the demo that there is some latency thing that comes up. So this is actually just the time it takes for the information to travel through your network. So again, this is a very simple example. Actual networks will be much complicated. We know how the internet and the network domain has grown in the last decades. So we expect the same with quantum internet as things move forward. Yeah. Okay. So even for swapping, we have this probabilistic nature. There is latency, there is swap degradation parameter, which I talked about, and swap will also fail. So if it fails, we try to reattempt. Okay. So quantum network simulators are a very essential tool towards the journey of actual functional quantum internet. So that's a dream. It's a long way forward for quantum internet, but not that far as well. With the progress happening with the faculty that are getting involved, with the students, smart minds in India and over the world, we see that a quantum internet is going to become a part of our life soon. But before it does, it's very important to have something like quantum network simulators, right? So they provide an understanding of designing, optimizing, interplay between quantum hardwares and protocols. So everything actually I've not broken down. So everything here is a mimic of a quantum hardware. So there would be over there would be something which will be sending a photon. Then there would be a detection happening and many other physical processes that are actually there behind the scenes. And this will definitely accelerate something like quantum network simulator. Why I took this time to break it down and see the working of it, because this is at a fundamental research stage as well as product stage. So there is a TRL level that we are trying to get better at in this domain of quantum. So the idea here is that wherever we are, it is at a stage where it can always be improved with young minds coming in and contributing to say some innovative aspect. Maybe someone comes up with a better swapping protocol, so that would increase your simulator performance. But eventually, your functional quantum internet is the goal that we are looking towards. Yeah, a vision for quantum future. So morning, Nilesh talked about quantum cryptography. It was well backed by Riktim on quantum communication, and we understood that if quantum offers threat, it also offers solution. But in this case, quantum internet is a completely, physics-backed phenomena. So we take into account laws of nature. We try to manipulate them in our favor. We want to create a network which will help us, but we will take help from, physical laws. So there will be hybrid systems again. So hybrid, we talk about this word every now and then, because when we talk about quantum, people assume that quantum is quantum. No, quantum is hybrid. Like there will always be classical things that will be happening after you measure. Your measurement results are zeros and one, which are again classical. So it is always going to be a hybrid architecture and hybrid system, right? And simulators like QNT-Sim, which is our product, through their ability to model this complex quantum phenomena, user adjustable parameters. So this is a very useful thing for actually industry as well. So a company wants to create quantum internet, wants to be the first in the world. So they need a simulator first. So they will first get the simulator, do the complex, they will adjust the parameters, see how the network simulator does, and then maybe invest in the actual hardware. So all of these things are actual hardware. Your memory is costly, your channel is costly. You want to make sure that memory also has high fidelity. You want to make sure that memory has high efficiency. So all of these things, we want to keep it ideal, but as we know, quantum is probabilistic, and we can only try to keep improving upon this. So that's why a network simulator is very important to keep increasing the understanding of how the quantum internet would look like in the future. So before we go there, we want to understand the current state of the art. Yeah. So that's it. I hope you guys learned something from this. Thank you for attention, and if any questions, please ask. And next next Riktam will help us with the demonstration of QNT sim. So before that, if you have questions, please ask, and then we'll just take a 2-3 minutes break so that we'll just connect the laptop and yeah. Yes.
Noise.
Sources of noise. Okay, great question. So, sorry. Yeah. So for our physical process, like you talk about, say, photon, you can lose the photon will decay like that. So what are the sources of noise means? So sources of noise means like you're actually any physical phenomena that you're doing today is not perfect. Look, so your quantum state itself is a fragile state. So your state is decoding due to noise from environment. So when we talk about, say, optics lab, which people work in, so you don't want any of the light also. So you close the you isolate yourself in a dark room that we call, and then you want to make sure that you're taking light only from the laser and all. So sources of noise are actually just interaction with environment. So any kind of interaction with environment will incur noise into your physical system right now. So it's one great thing I can tell right now is that transistors, that okay, above 5 volts it will be 1, below that it will be 0. But if you talk about the same type of thing in quantum, even if you expect okay, above 5 volts it should be 1, it's a probabilistic phenomenon and it may not be because of, say, noise and all. So that is where quantum gets a little tricky, but also has its advantages. As we'll look, I think there are very interesting lectures to follow on quantum algorithms after this. So this is where you will learn a lot more about the algorithms which actually put us in this field forward. So the idea was that even despite these intricacies and challenges, quantum algorithms provide a very promising future. Yeah. Okay. Fidelity, ma'am. So idea was, as she talk about noise, no. If we have an entangled state, state, say 5 plus, which looks like 0, 0. Plus 1, 1. But when I'm physically trying to do this now, it may not be the case. So physically, actually, you might get something like 5 plus, 5, 1 plus, just trying to name it. So this 5, 1 plus and 5 plus, how close they are, that is fidelity actually. So this is with error. So let's say they are completely like not close. So fidelity would be 0, because in the sense that this is completely, there is no relation to 5, 1 and 5. But yeah, 5, 1 plus and 5 plus, yes. But say example, this error is less. So say fidelity is 0.99, it means this is very close. It's almost 5 plus. So that's what this fidelity is, something which we want to be high. We want it to be high. So actually, whatever we are doing here, we are transmitting information. So whatever information that we are transmitting, we want to make sure that the information is not lost. Like if we'll see in the demo, there is something that we ask the user is target fidelity.
Multiple times in step 3.
Okay, that is just purification that we're doing multiple times. So the idea is, good questions. Thank you. Keep asking, please. Over the FDP, we are happy to answer. So this protocol you can do multiple times to just increase your fidelity of the pairs. So first concept is fidelity. So fidelity is to account for how, actually fidelity will also account for how good your network is. So eventually your target fidelity is something that you want your network to be like, say, 0.99 target, but it may not reach. But to at least go towards it, what you will do is, so if you look here, entanglement, generation, swapping actually reduces fidelity. And swapping also has a low success probability. Actually, it's not like very high, 64%. So purification is where actually you are increasing the fidelity. Say I use percentage, but it's just 0.95. So say this is 0.95 after step 3, after multiple purification. But after swapping, this might reduce to say 0.92, like that. So the idea is that this is a very important point over here, that purification actually helps you increase fidelity. So to reach a target fidelity, multiple times you do purification. So I remember we are doing some simulation. So we did like 7-8 times. So we are able to reach a fidelity close to say 0.95. So like that. So idea is that purification will increase the fidelity, and the network is, there are many other things, but it will be judged from, say, your target fidelity. So you want the whole network to have a target fidelity. Okay.
More
Right.
the fidelity, more pure.
Yeah, more fidelity, more pure, or more right now it's not like if I say something to you in quantum language, it may not go. I say hello, but it might go hello, hello. Like some break noise would be there, right? So Fidelity is trying to make sure that how close the information I'm trying to send you reached you. If I wrote hello and sent you, maybe my O is lost. So sorry, but I sent you hell. Okay, so it is as close to hello. It's a 90% close, but the information is lost. No, hell and hello में तो फर्क हो गया ना, like that. So that's what your target fidelity. Yes, it is to make sure that information is as close to what you expect. Yeah. Okay, so I think good that we had few questions and Riktim could take time to set up our simulator. So I'll leave to Riktim now. Thank you for listening. Thank you. Okay. Can we not take it up? Then it will be out. Pin to the screen. Can you try that? Ah, okay. Huh? Is it fine? Coming up? Okay. All right. So, hope I'm audible to you all. So we'll have a very short demo, like then we'll have tea, nice tea. Okay. So basically what we'll see is how these network simulators can help us to design networks. Okay. So it's a typical network that we can have, very small network. It can be very wide also, but let's understand the small things and then we'll connect it to larger things. But before that, just to add one perspective from the previous thing, which is, so Aniket explained to you about all the physical parameters, but let me do a connection to what we know in computer networks today. So in computer networks, we can have, if we follow the OSI model, it's a 5-layer network, right? 5-layer architecture. And to design the quantum networks also, we use this 5-layer architecture. Why? Because we don't want our quantum networks to be isolated. We want a coexistent. So it has to map, right? There has to be a one-to-one mapping. So even in quantum networks also, we have 5 layers. The first is, I'll do top to bottom. First is application layer. Then we have transport. Then there is network layer, then data link layer, and finally physical layer. What I'll try to do in these 5 layers only, I'll try to fit my quantum components so that it can coexist with the existing network. Okay, so let's go from the top. Like for example, I am a user. So what can be an application? It can be anything like, we have seen QKD, right? So it's an application. Then we have also talked about QSDC, QSS, which is quantum secure direct communication, secret sharing. These are all applications which sit in the application layer. Below it, we have transport layer.
So what transport layer will be doing, it will manage requests from different user. Like if multiple users are trying to ping the network, then it will manage like whoever is coming, like we have FIFO and first in first out protocols, right? So all those things will be managed by the transport layer. Next is the network layer. What network layer will do? For example, here I'll if I just make a graph over here, let me just, for example, I choose a mesh topology and I increase the number of nodes. I'll just take something. So for example, now in this, I want to communicate between node 1 to node 6. Now you can see there can be couple of different routes it can take. Like it can either go this way or it can choose this way also, right? Which is the best part to choose? We have routing protocols today also, but how will those routing protocols be applicable here? Not exactly, because the quantum resources are alive only for certain amount of time, very small time. After that it will decoher. So we have to take into account those parameters. We have to take into account how much resource is available for how much time, so that we can tune in our routing algorithms properly. So those routing algorithms, network routing and reservations come in the network layer. Okay, so reservation is like, for example, this path is decided. The moment it is decided, all the resources in this path will be reserved. So what resources? We saw photon sources, detectors, routers, switches. We discussed couple of things, right? So all those resources which are required for the protocol will be reserved. And the routing decides which path to choose. As simple as that. Next is link layer. Like the name suggests, it will create links. Now, you may ask, why not directly 1 to 6? Why these two fancy nodes? These are intermediate nodes. If you remember from the swapping example, I explained that if you directly connect them, you may lose everything. You may not get anything. So it's good to have intermediate nodes which acts like swapping stations. Like you swap, consume something and create long distance links. So these are these intermediate links or repeaters, quantum repeaters, which helps you to create long distance nodes. Okay. And this link layer takes care of this part. So it does three things, which Aniket explained in the last hour: entanglement generation, entanglement purification, and finally swapping. So you will appreciate now why purification is necessary. What will happen? Every quantum computation or any kind of gauge that I apply, even if you are working with quantum computing, you will see the more number of gates, the lesser fidelity or lesser certainty of the state you get. Why? Because we are trying to constantly implement some measurements on it. Very small, not measurements, but computations on it. That decohers the state. The same happens here also. The longer my node, the operations will degrade the state. That's why I will need purification. It's like collecting a bunch of, like he gave a good example that we have unfiltered water, like you have a lot of them and you finally filter it to get a small chunk which is very good. Same thing. So if you have a lot of them, like for example 1000 unpure entanglements we have, which is not very high fidelity entanglements, of that we will purify it and get finally 1 or 2 good entanglements, which should be sufficient for my protocol. That's how we will design it. So entanglement generation, purification and swapping. Once all these things are decided, finally we'll talk in the physical layer. Physical layer has all the photon sources, detectors, then memories and many other things like quantum channels and everything. Like today also we have in physical layer all the transceivers, all the senders and receivers objects. So this is what is going in the background. So the moment I'll click it, you will see. So let's choose an application which is like, let's say E91 QKD. So we looked into 2 applications, right? BB84 and E91 QKD. So we'll try to distribute keys between node 1 and node 6 via simulation. And when I execute it, everything will go in the background, you will not see it. That's why I've explained it. What is going in the background? You will see just it's loading. Okay. So in this graph, let me just choose one sender. and one receiver. Okay, and let's say key length of 5. So I'll now just run this application. So in the background, what is happening? It is first selecting the application, which was my E91 QKD. Then it is going into the transport layer, going into network layer, finding the route, going into the link layer, doing entanglement, generation, purification, and swapping. So I demanded 5 key size, right? Which is like 10111, something like that, of length 5. Okay. So this was creating a problem in the morning also. Let me see. We should be able to fix it. All right, let me just do it once again. If we are lucky, we'll be able to see it, but like Murphy's law plays in, it was working fine till the morning, but afternoon something happened and it's showing some errors. But let's see. But what we'll get is at the end, I'll just tell you, okay, we are lucky. It's not probabilistic, but our internal servers are sometimes creating problem. Anyways, so let's see what happened. Okay. So first parameters is execution time. So execution time is like how much time the protocol took to execute. That is the simulation, not the actual thing. Okay. Simulation time was 21 seconds. Fidelity, the important parameter. Okay. How many of you didn't understand fidelity? Just raise your hand. I'll tell you in a very simple thing. Everyone understood? You didn't understand? Fidelity is what? You prepared a dog, but you got a cat. That is worst fidelity. But if you prepared a dog and if you get a dog, then it's high fidelity. So the closer the number is to 1, that is a high fidelity thing. The lesser it is, it's a low. Why we are worrying about fidelity? Because quantum states are very fragile. That's why we need them in a very pristine manner so that we can use them, right? Because just a simple example, like I was talking about, we were talking about the superposition state, right? H plus V by root 2. Now just imagine if the probability shift by a little also, this state is gone, right? And we saw an example yesterday also with the Hadamard gate, which was like the gate was being applied and over time it was just decaying. So just imagine if I've prepared my state and over time it has just decayed or decohered, then it is not usable. That's why fidelity is very important, because all my assumptions are based on this state. And if this guy changes, my entire protocol is of no use. That's why fidelity is an important parameter. And we desire as high fidelity we can get. That is the fidelity. Next is success rate. Success rate tells about how much I requested and how much I got. And finally latency, which is like the classical channel latency. I'll just scroll a little.
Decoherence.
Yeah.
Decoherence. What we are losing the message.
No, the state changes, which is, suppose this was my state that I have prepared, and with decoherence, it has become something phi. Okay, so more plain language, if I say, suppose this is the state I have, which is H, or we are familiar with it, right? Like the horizontally polarized light. Okay. So over time, if it becomes a diagonal polarized light or maybe something different, then this is not H, right? But I designed an H, but over time it has decayed to D. So you will ask me like, how is it possible, right? So I'll just tell you that in a short.
Because of what?
Because of the environment. There is an environment. For example, photon only, I am sending it. So there is an environment which is there are dust particles in the environment, for example, and they are trying to constantly interact with the photon. So even though the photon was prepared in this state, constantly if I try to poke it, it will just change, right? And after a certain point of time, it will change so much that I send this, but I'm getting something this in some random direction.
Energy is, we are losing the
Yes, we are losing energy is there, but even like energy loss is also not so like drastic change. It will always be in a band. So I may not see any change in energy, but what I'll see, the photon polarization has completely changed. Like if it is changing energy, okay, so first thing is photons are such particles which interact least. That's why optical fiber cables are replaced by copper cables today. So copper cables, what was the problem? With high data transmission, the wires used to get heat, and heat is acting as a noise. But with photons, why we are using geo fiber cables today? They are sending photons, and those photons do not interact with the matter so high. That's why they are able to send it to longer distances. Okay, so it means that the energy won't change a lot, but the property of the photon in which it was prepared may change. Do you get it?
We regain the properties by keeping the intermediate.
Yeah, exactly. We are preserving the property by creating multiple intermediate nodes, so that whatever my longer distance goal is there, I can achieve that. That is what we are trying to do. Yeah, yeah. So I requested for 5 kilon size, right? So here you see, out of lot of entangled photons which was shared, these are the highlighted ones are the bases when they actually chose the same basis. So I if you recall, I said like Alice prepares in some basis and Bob measures in some basis, which is again both random. So once they have done their process, they will just communicate over a classical channel that okay, this was my basis, what was yours. So they communicate that. So that is what we are seeing here, that this is the sender's basis, completely random, and this is the receiver's basis, which is again random. And on the basis when both of them match, the keys are same. So that is how this random key is generated. And if we run it completely multiple times, you will see it's always different, always coming out differently. So like this, we have lot of different protocols also. Like here we have like 10 different protocols. I won't go into all of them because what you will see is the final results only, similar to that. Important was whatever we discussed up to now, like what is going in the background, because in the foreground it's just results, and you get to play with certain parameters also. Like for example, here you can change the number of memories. I will not talk about memories today because tomorrow we have a session on quantum storage, and Devendra will be talking about what is a quantum storage unit. Like it is like storing qubits. Okay, that's a very interesting thing, but we can change such parameters. Like we can change the channel distance also. We can change how much attenuation the fibers are creating. Also, we can go into more advanced parameters also. Like here, where is the, okay. Like here, if we go, then we will have lot of more parameters also. Like, so in this way, okay. Like if you go into this, if you just zoom in, we'll see memory frequency, memory expiry, memory efficiency. So we can basically change all these different parameters. We can set up different topologies. We can create a network of our choice, and we can finally simulate it. So in a nutshell, what have we seen today is basically how quantum networks can be designed, how they can be played around with without actually having a hardware at your end, but simulating how different protocols or algorithms for cryptography can be implemented. So that is what we wanted to deliver from this session also, like how you can design quantum networks and how they can be used for different applications. So, all right. So that's all. And if you have any questions, we'll be happy to take. By the way, that's all for communications part. Now you'll have computing. Okay.
That Z value is not same.
What was?
The sender end and the receiver end. Z value, once it is 0.
Oh, that was exactly opposite, no? Why? Because we are using this entangled state. Wait, I'll tell you. So there are 4 Bell states. Okay. 2 of them are this, and 2 of them are this one, right? Like plus minus plus minus. I am just writing it in a way. So it's like phi plus minus and this is psi plus minus, right? So 2 of this kind, 2 of this kind. What in the simulator we have used is this one. That's why when Li's got a 0, Bob will get a 1 because they are opposite. If we had used this state, when Li's got a 0, Bob would have got a 0. That's why you will see they are exactly opposite. That's how we are doing.
Same.
Yeah, because they are entangled state. I have the knowledge of the entangled state, right? Like which entangled state I have prepared. So because they are opposite, if I just want to generate the same key, what I will do after they are opposite, I will just put an X gate so that it's just reversed. So it's the choice of the user. We can select any of the Bell state and do it. Yeah, correct, yes. Even we like switch from this Bell state to the other one.
Easy to understand.
Yeah.
0, 1, 1, 0, it get confused a little bit.
Ah.
When it's new. I mean, you are new.
Yeah. But it's just like opposite pairs. And I best understand it by twins. They are always opposite. If one is very quiet, the other will be very naughty. So this is more like relatable. Okay. Any more questions?
Basis.
Yeah.
Z bits.
Sorry?
Bits is BGA for protocol.
Ah.
When you pass to
Hmm.
the key. So,
Yes.
some basis.
Yes.
How this transfer something.
Okay. So, there are 3 different bases we use, and those are all 3 axes of the block sphere, X, Y, and Z. Okay. If I draw the block sphere, I call this as my Z, this as my X, and this as my Y. Okay. If any state, let's look at polarization of light, because we have been talking about light from the morning. Okay. And it's easy to see polarization also. If I prepare a polarization in Z basis, it can get 2 states. Either it will be horizontally polarized or vertically polarized, like pointing this way or this way. If it is prepared in X basis, it can be this state or this state. Okay. This is Z, this is X. But if now there is a phase term added, which is the complex number iota, or then we prepare the state in Y basis. How they are different? This is this is V, this is H. If it is in middle, this is D or this state. If it is this way, then it is this state. Okay. If there is an additional phase to it, which is in the complex plane, then it is H plus IV and H minus IV. But you will ask me, how do I see it or where do I see it? In 3D movies, the goggles that you wear, they play around with circular polarization. So this is called as left circularly or maybe right, and this is right circularly. Okay. So these are like, this is D, this is A, this is H and V. So this is how I can prepare different polarizations. And how physically I do it, I have 2 optical components called as half wave plate and quarter wave plate. So when these wave plates are put at different directions, they create certain polarizations. Okay, it's a basic optics based phenomena. If it is put in certain directions, it will create the states. Same with quarter wave plate. So quarter wave plate helps us to go into circular basis in the left circularly and right circularly polarized slate. Understood, right? Little. Okay. Okay, thank you all.
One here. So I'll take this session. I'll try to introduce this Deutsch-Jozsa algorithm, which is a quantum parallelism, which shows a parallelism, quantum parallelism. This actually, there was a fact behind it, that why this came into the picture. Because this Deutsch algorithm first came into the picture in 1985, around 1985. Because in 1982, actually many things were going on in 1982. In 1964, first of all, we got to know about the Bell inequality, which actually, okay. We got to know about the Bell inequality, and because earlier that people were doubting about the entanglement. Of course, this was a physics phenomena. Physics people were able to understand it with some experiments, okay, but still those were in doubt, because how this thing is happening. Like earlier we said, some hidden variables must be going on in there. So entanglement was not clear to many of the scientists even, okay, and it took them around 64 years to understand entanglement, okay. Bohr was completely sure that there is some kind of thing is happening, because he only proposed about the quantum photons, but even Einstein was there that there is nothing like entanglement is happening. How could someone can send something to this far, okay, without even communicating directly, right? So I would not say that these are the concept can be understood by anyone in a one go. I'm trying to give an example here that these are the things, these quantum things are which are not even visible through eyes, cannot be understood in a one an hour lecture or half an hour lecture, okay. So I'm trying to say currently that just be with us, try to understand and try to ask the questions as many as possible about these phenomena, and know these things take time, okay. So where in 1964 Bell inequality came into the picture. That was showing the entanglement, that was proving the entanglement by doing some computation, by doing mathematics, okay. So at that time the people who were from computer science background as well try to understand that, okay, there is some kind of phenomena, entanglement that is happening, and this is how we can prove it using that Bell inequality. And seeing that Bell inequality came into the picture, okay, Feynman at that time was very good at teaching the things. He was trying to understand this quantum physics as well at that time, and of course he understood it as well, and he was working in doing mathematics only. He was doing physics. So in one conference he proposed that, okay, why not if we are saying that classical physics is very much different from quantum physics, because quantum physics is always about those those tiny particles which we cannot understand with our naked eyes. So those are the basic phenomena which we are not able to see with our naked eyes. Those phenomena can help the bigger things to happen, of course. So that means this nature is quantum, okay, because if we are saying even in a fun way, if you are saying that if you are even making simple sound, and somewhere on this earth, in this world, some other thing is changing. So those are some interconnection is going on. So that means he somehow thinks in this form that everything in this nature is quantum, okay. So why don't we are relying on these classical computers? Why don't we come up with some quantum computers? If we're trying to simulate this nature, if we are trying to understand this nature, why we are using classical computers? Why don't we use quantum computers? Okay, so this was his idea. And at that time, Deutsch Dosh was the first person who thought that, okay, let's think about it, what we can do with quantum computing. Okay, entanglement was the phenomena that has been proved, that has been proven using that Bell inequality. Now, how we can use that quantum computing into solving some of the problems. Okay, the first thing that comes into our mind, if we have something, if we have proposed something, if we have constructed some of the instrument, now we will think that now let's see what it can do. Okay, even a child, if he comes to know with a different phenomena, he comes to know that okay, this can be done. Okay, first thing is, if he comes to know, okay, this is how you fire a matchstick. Now let's see what we can do with it. Okay, he goes and fire around the house. Okay, so even a small child can do these kind of things. Why don't we can do with the quantum computer that we know? So at that time, Dosh algorithm came into the picture, and of course he was trying to understand what kind of problem we can work with this. Okay, so that he come up with a problem of his own. So that was a problem of finding a function if a function is constant or balanced. Okay, so this Dosh-Jozsa algorithm is an extension of Dosh algorithm actually. So that's why we just call it Dosh-Jozsa algorithm. And first of all, this was a hypothetical problem. There was no link to the physical world with this problem. There is no link to the physical world. But the concept behind it, whatever the function he has used in this, whatever the circuits he has used, somehow some other algorithms took those phenomena, took those functions and used it some other algorithms actually. So if you understand it, so he considered that there is a function, okay, and that function is that function can be a constant or that function can be a balanced function. How do we define that function as a constant or balanced? So later on, of course, we will try to visualize how the parallelism is coming into here. Okay, so first of all, let's try to understand the problem itself. So function is a constant or a balanced. A function means it can take some value and give us some output. It takes an input, give us an output. So in here, of course, first this table cannot be understood because f of 0, if I am providing 0 as an input, if a function is constant, that will give me 0. Okay, and even the function is constant, even if I am giving f of 1 as an input, it will give me 0 because the function is constant. It will always give me one value. And if it is giving me 1 as an output and this function is a constant, if I am giving either 0 or 1, it will give me 1 as an output. Okay, that is constant function. Balanced function is, it tries to balance the output. For f of 0, it will give me 0. For f of 1, it will give me 1. Means half of the time the output is 0, half of the time output is 1, or the other way around, f of 0 with 1 and f of 1 with 0. So this is a constant or a balanced function. Understood? Now the problem here is, of course, this function is a constant or balanced. Using a classical computer with our own thinking, how do we understand a function is a constant or balanced? We try to give it one input, see what output it will give me. Now, with a single input or with a single output, we will not be able to understand that if the function is a constant or a balanced function. Okay, we have to give another input to it. If I'm talking about 2 bits, then we have to give another input to it. So after giving another input, now because I knew that what input I have given, what output I have got, I try to give another input. I have given f of 1 as an input, f of 1. It will give me, if it will give me another output, that means I understand, okay, the function is constant, balanced. If it give me the same output, that means my function is a constant function. Okay, so now with the basic phenomena, with the basic understanding, or we can say with the basic classical computation, we have to give 2 input at least, or we have to measure 2 inputs. Okay, so kind of, if I'm getting the output, that means I'm measuring it. Okay, so we need at least 2 input, or we need to measure 2 outputs, 2 bits in here. So Dosh come up with the function, entire function. This is entire function. Let's say this is entire function. So Dosh claimed that with only one measurement, I can tell you that whether the function is a constant or a balanced. Okay, so that means where we require 2 inputs to understand that function is a constant or balanced, Dosh claimed that with only one input, with one measurement, I can tell you the function is a constant or a balanced. So that means he did something parallelly. Okay, so that's why this algorithm, Dosh algorithm, is also known as parallelism algorithm. Okay, because this was the very first concept that made us understand how the quantum phenomena come into the picture. So I now try to do all these calculations on board. Okay. Okay, so this is a Dosh-Jozsa algorithm. So in here, Dosh-Jozsa algorithm is a generalized algorithm. There are n number of inputs here. This is Ancilla. Okay, Ancilla is some additional input that we give in quantum computing to try to understand try to work with these circuits in better form. Okay, and if I'm writing this /n, that means there are n number of wires. Okay, because I'm giving n number of inputs, that means I would be requiring n number of wires, and H tensor n means on each of the wire this Hadamard gate is we are applying, and this is going into this particular black box. Let's say this is a black box, and at the end I'm getting some output and applying Hadamard tensor n type of n number of times I'm applying Hadamard and then measuring it. Okay. Now, what is happening over here in a I'm saying it is a generalized because the example that I gave you, that was only of 2 bits. Okay, or we can say 1 bit. Okay, quantum mechanically 1 bit. But in here, if we have n number of inputs and we try to check for those n number of inputs how the function is behaving. So for that case, classically we would be requiring at least n by 2 plus 1 number of measurements, and in here of course, and in here we would be requiring only half of the inputs, okay, for the measurement purpose. So first of all, I'll let you know what Dosh algorithm is. So Dosh algorithm is very similar to it, just that the n number, we are not considering the n inputs. Okay, so let's say this is x, this is y, and this is some unitary function. Overall, this is a unitary. This is an oracle, we can say, in quantum computing. Okay, again applying Hadamard gate, we are getting some output from here, and from here we are getting some output. Okay, but in here what this function is doing here, y XOR f of x. Functionality of this oracle is this: it keeps x as it is and it changes y to this form, y XOR f of x. Now let's try to understand that how Dosh claimed that with one measurement only it can make you understand that function is a constant or a balanced function. Now let's say this is 0. If Hadamard gate of always, if we are doing some quantum computation and we are applying some gate, we write that gate on the left hand side and acting on 0. So Hadamard gate is acting on 0 here. Okay. So that means what is happening? Yes, and this is 1. Of course, we have to apply Hadamard on it as well. So Hadamard on 1 minus of 1 by root 2. Okay, so this is the basic functionality. Okay, we have done Hadamard gate transformation. Now, I'll just write here what is happening at each step. Okay, so psi 1, at psi 1 we would be having 1. Okay, 0 and 1, and we are applying Hadamard to 0th qubit, Hadamard to first qubit. Okay, at psi 2 it would be 0 plus 1 by root 2 and 0 minus 1 by root 2. This is it. Okay, basic. So try to keep in mind, this is the first qubit and this is the second qubit on the second wire, first wire. Okay. Yeah, tensor. If I forgot somewhere tensor, try to understand that there is a tensor in here. Okay, this we got to know. Now x is as it is, y is changing to y XOR f of x. Okay, now let's say this is here, psi 3 is coming up. Okay, 0 as it is. Now 0 is going with 0 and my 1 as well, of course. So that means now y is changing in this form, because x I have taken out, y is changing in this form. So that means 0 minus f of 0, f of 0 because x is 0 here. Okay, minus 1, sorry, this is XOR f of 0. This is understood? This is y, this is f of x, and x is out here, and this is y, and this is y. 0 minus 1 XOR f of x. Okay, understood? This is very basic. Plus, for the same case, 1 for the 1 case. Now y is 0 XOR f of 1. Now we know that, now we know the XOR functionality, what it does. If 0 XOR 0 is this, if f of, I'm now considering, just considering, if f of 0 is 0, that means this will be 0, right? And if f of 0 is 0, that means this would be 1, right? So that means what it becomes? This becomes here 0 minus of 1, right? Now let's say if f of 0 is 1, in that case this will become 1 and this will become 0. Okay, so in that case this will become 0 earlier I considered that this, I consider that if f of 0 is equals to 0. Now I consider that if f of 0 is equals to 1, in that case it will become 1 and this will become 0, right? So this equation will become 1 minus of 0, both of the cases. Okay, for f of 0, f of 1 equals to 0, 1. Okay, Okay, now this becomes 1 minus 0. Now this is now not we work with qubits. We have to take a negative sign out so that it can become 0 minus of 1. Okay, now this is we are familiar with. Now what is happening is we kind of understand that there is some minus sign coming up if depending on whatever the value of f of x is, and x is coming here. Okay, now if f of x is, if x is 0, that means this will be x as it is. If x is 1, that means minus sign will come up here. So instead of writing this big equation, we can dissolve this particular equation to this particular equation. Okay, so what we can write here is, okay, oh, so what I can write over here, okay, okay, just I have kept this 0 minus 1 as it is, otherwise I have written x as here. Okay, okay, so I have take what I can do, just take it as common 0 minus 1 by root 2. Okay, now because we were having this as 0 plus 1, okay, now let's understand that if the function is constant or a balanced. Now because x was in this form 0 plus 1 by root 2, we can just write f of 0, 0 minus of 1, f of 1, 1 by root 2, and 0 minus 1 by root 2. Okay, this is easy to understand. Okay, now I'm at this point. I have not touched this Hadamard gate. I am just here. I have applied this y or f of x. Now let's say our function is a balanced function. Let's say for the balanced case, f of 0 is equals to say 1, f of 1 equals to 0. Now let's try to put it over here. Okay, if we try to put this in here, we will come up with 0 minus 1 by root 2 and 0 minus 1 by root 2. Okay, for the balanced case. Okay, if the function is balanced, now I have considered computationally if the function is balanced. Okay, now if I now apply a Hadamard gate over here, on the first qubit it has written that we will apply a Hadamard gate. So that means it will become 1, and we are not bothering about this the second qubit. We are only interested in the first qubit. We are only measuring the first qubit over here. Okay, so I have applied Hadamard gate. 0 minus 1 by root 2 is converted into 1. Okay, this is the basic phenomena. So it says that Dosh algorithm, now this is single one, and now if I measure it, it will give me 1. Okay, there is no quantum qubit left in here. This is not in the superposition. This is a single state. I am measuring it. Okay, this will only give me 1. If it is giving me 1, that means the function was balanced. Okay, and if it is giving me 0, that means the function was constant. Now I have taken the assumption that function was balanced, so I came to 1. Now if I take the function is constant and put those values over here, that means I will get 0. It shows that with a single measurement, we are able to understand that if the function is a constant or a balanced. Okay, so this was proposed by Dosh, this simple functionality. Okay, and this later on is extended to a generalized algorithm, which was known as Dosh-Jones algorithm, where we consider that there are n number of qubits, n number of inputs we are taking into account, and we are trying to understand if the function is a constant or a balanced. The problem statement is same, just that they were trying to understand if this same thing is working with the n number of inputs or not. So for that, now we understand, okay, what is happening. I have shown this function because those are the equations. For n number of cases, we would not be able to do all those Hadamard gates and all those unitary function. So I have shown you the simplest case. Of course, we are initializing with 0. Then we are applying Hadamard gate. N times we are applying. So we are not considering any 0 plus 1 case over here. We are just taking that there is a x by root 2 of n. Okay, because root 2 is also coming into the picture. N times. So we are applying root 2 power n. Okay. Now, because we came to know that if we are applying Hadamard gate over here, and later on we already have the unitary function in here, we come up with this particular equation. We got to know we can get onto this particular equation. For the n number of Hadamard as well, this equation would be the same. Minus 1 power f of x, root 2 power n, and this is the y part. Okay. Now, okay, this unitary, in here we have applied the oracle or we have applied the unitary function. Now again, for this particular qubit, we have to apply the Hadamard gate. If we are again applying the Hadamard gate, so again the same thing is coming in here. So this is f of x, which is y XOR f of x. So this is x dot z, which is also can be written in that particular form. Okay. So we are applying x Hadamard gate on x, and this is the thing we are coming into here. And of course, because that was, we are only applying the x gate on the x gate, Hadamard gate. Another thing, minus 1 power f of x by root 2n is still there. So it is coming in here, xz dot plus f of x. So this particular equation at the end we will get. Now, if we measure this particular equation, if we put what the x value is, okay, if we put what the function is, if the function is a balanced or a constant, and if we try to resolve this particular equation, we will see that if all the n number of inputs we are able to measure it in 0 state, that means the function is constant. If we are not able to measure those in 0 state, all are 1, that means those are balanced state. That function is balanced. Now, practically what is happening over here, we are able to get zeros, but for the balanced case, we try to see that if there is only single one is coming, apart from all zeros, any state is coming, that means the function is balanced, practically, okay? And theoretically, we say that, okay, if the function is giving us all 1, that means that was balanced, and all 0, that means that was constant, okay? So this was Dosh-Jones algorithm, a theoretical implementation. A theoretical Dosh we will see on the same day, but right now we will see another day. So that's why I told you this Dosh algorithm is very simplest algorithm. This is the very first algorithm which was given to understand that how quantum computing is working. Earlier there was phenomena that superposition is there, and now from this we can understand that if there is a superposition, that means we can implement one function to all the qubits, all the possible bits that we would be having. We can implement that particular function in one go. Okay, earlier in classical computing, suppose we have 0 0, suppose there is a 0 0 0 1 1 0 1 1, and we have to apply some operation over here. Say this is the operation. So for the classical case, we have to apply this to 0 0 0 1 1 0 1 1. Now in here, what is happening in quantum computing? We can write it in superposition form. Okay, and this x function can go in one go. So this is the thing. Is the same thing is happening over here. With the help of Hadamard gate, we made that particular state as 0 plus 1. Okay. Earlier instead of this in classical computing, we had to apply that on 0 and 1 as well. Both of the cases. Of course, not this form, this way, in this way. So that is a qubit representation. Okay. Now with the help of Hadamard gate, we made it in superposition and we applied all those phenomena in one go. So that's why this is the concept, Dosch gave the concept of parallelism. The how superposition, even the superposition phenomena, we can make use of. Otherwise, everyone is only talking about entanglement, but superposition is also there. Superposition can also help us in some way or other. Okay. Is there any question in this? I think I've gone into very detail of this Dosch algorithm.
We need to again work it on because then only we'll get to know really what we probably we have to apply the gates.
Okay, so that's why I have taken this notebook, because every time I try to understand even though I have gone through this algorithm a number of times, I have also written this in my thesis. Still, again, if I am going through this Dosch algorithm, if I am teaching someone, if I am trying to make someone understand about the Dosch algorithm, I again go to my notebook and try to solve all those equations, because understanding that if f of f is 0 is 0, some assumptions are coming in here. So those assumptions always you have to write on some notebook and you have to understand what is happening behind it. So that's why if you are working with quantum computing, it's a good practice. You always do everything on paper and pen. Okay. And if any question, anyone? This Dosch algorithm actually, I ask you to try to do it on your paper. Okay. Because this particular phenomena will also help you in Grover's algorithm, and the implementation of this algorithm is a little bit different from what we understood from here.
Little contradiction. You said that we will try to understand given an input whether it is balanced or constant. But when we look at here, you are talking if it is a balanced, we are taking 0 over here. And
Yes, of course, because I was trying to resolve that what this unitary function is doing over here. Okay, so that's
we
why.
are making an assumption.
Yeah, this we have made this assumption to do it mathematically. Okay, and if I gave you this oracle, I gave you this. This will tell you if the function is a constant or a balanced. You give it some input. You measure it, and based on the output you are getting, okay, you are getting 1, that means it is a balanced. You're getting 0, that means constant. Okay, now what that particular oracle is doing?
No. If suppose I gave 0, I am getting 0. You are saying that it is a constant. If it is 1, I'm thinking that it is balanced. What is if I am for the next thing, like second thing, I'm going to get again 1.
Yes.
So then the basic understanding of the beginning, what we thought will be different.
No. Actually, this I try to tell you. Okay, mathematically you understood this. Okay. Again, if you give this as a this same unitary function, the same thing, you will get 1. this is going on with the same, yeah. How many number of, if whatever you give, this particular, for this particular unitary function, if it is first time it is giving you 1, with anything you try it on, it will always give you 1. Okay, this I have considered. Now, I don't tell you that what the mathematics is doing over here. I'll just give you this oracle. Whatever input you are giving it, it will always give you one thing, because I knew, I designed it, it will always give you the balance function. Okay. Here I have just, for sake of understanding what is going on in behind mathematically, that's why I came up with this. Okay. You work out on this, take the different examples, take different balance, because there is this is also a balanced function. Okay, so try to take this assumption as well. Another assumption of constant as well you can take. So there are different assumptions. You will see that with each and every assumption, you will find the output. For this assumption as well, you will find the output as 1. Okay.
Whatever it might be 0, 1 or 1, 0, we are initially applying third part gates.
Obviously, everything is going in. Yeah, that you understood very, very quickly. I appreciate that. Really, actually, this is what is going on. Whatever you give it, it will definitely give us the same output. Okay. So, from the last class, is there any doubt on the teleportation? Because I have a video, animated video. I can show you what the teleportation is actually is, how it is working. So actually this is a teleportation video. I have seen one. I found it very relatable from the previous case what we did. So this is a teleportation. We understand what is happening. So that person over here moves in here. It is destroyed from there. It appeared here. This is a teleportation. Very basic teleportation. Now let's see how. Now I have muted this video. So quantum entanglement is like there is a connection in between two photons, some kind of connection which we are not able to understand, but there is a connection that even those photons go on in a different space as well, on different universe as well. Those would be entangled. Their correlation would be there. Okay, so this particular whatever photon is, if we measure it, it will be destroyed. It will be converted into classical bit. Okay, until unless we do not measure it, the entanglement would be maintained. Okay. So just let me tell you, let me remind you what we did yesterday. So if you remember, in Composer we had 3 wires, Q0, Q1, Q2, and I told you this is with Bob, this is with Alice, and these are entangled. Okay, and this is the qubit that Alice wants to send to Bob. Okay, so this is the same thing, it is coming up. So there are 2 photons. Okay, these are 2 photons which are entangled with each other. See, I don't know if you are able to understand. See, here in B there is a photon, and in here C there is a photon. Okay, this is with Alice and that is with Bob, and those photons are entangled. And Alice also has one photon, one quantum state, which she wants to teleport to C or to Bob, we can say. Okay. So now Alice is not measuring that particular state. Okay, that is a quantum state that remains as it is. Alice has generated, she will not measure it. Okay. Now what she can do here is, because she knew that B and C are entangled with each other, and she was smart that if B and C are entangled with each other, until unless she doesn't do any kind of measurement, this entanglement can be maintained. But what she can do? She can somehow make some computation with these. Her own qubit, her own entangled state, and the state which she wants to transport. Okay. Okay. Now, she does some kind of operation over there. After the operations, a measurement is done. Once the measurement is done, the information will be transferred. Okay, because the entanglement will be disrupted at that time, because she did the measurement. Okay, and that time because she did some kind of operations over there, the information would be transferred to C. Okay, for that particular thing, she has to convey whatever measurement output she got. She has to convey it through phone, through fax, or anything. Although the information transferred in a speed time, okay, light speed time, but the Bob needs to know what kind of output Alice got after the measurement, so that he can also do some kind of operations and get the exact output. Okay, so he has to do some kind of manipulation into the information, and after that manipulation can only be done if Alice will share the measurement output with Bob. Okay, so at this time, there is a whatever calculation Alice did, everything is disrupted, everything is distorted over there, but Bob will get the output. Whatever quantum state Alice wants to send, he will get it. Okay, so that means that if it is possible, there is a question that if it is possible, if we can teleport a man to another space, what is the answer? I want to hear any kind of answer. Is it possible? What do you think? Because we have seen in many science fiction movies as well that they do teleportation. Okay, so what do you think, if it is possible or not? Possible, of course, possible, but there is one condition, because till now we have teleported photons only. Photons means which we are not able to even see. Okay, so and after the transportation, someone measures it and knew that okay, teleportation happened. For a human being to transport, first of all, we have to convert that particular human to small particles, and then we have to destroy those particles here so that that human can appear over some other space. Okay, so for the time being, it is not possible. If someone come up with some kind of technology that person can destroy a human being from here, but with some technology can reassemble those photons in the same form the human was earlier. Okay, so in that case it is possible. Earlier it is it is not. Okay, Okay, so
With the quantum probably in future we can.
yes, biology mix up with quantum computers.
The image is also
Images all.
3-dimensional
Uh-huh.
for complete
Mm-hmm.
create
Uh-huh.
destroyed
Yeah, that can be thought of if we can understand that how to destroy and how to reassemble that person, reconstruct any kind of thing, any kind of photons are easy to reassemble. But any other thing, even a bottle, even a plastic bottle, to reassemble it in the same form, if we are getting very minute particles of this plastic bottle, we would be coming up with some kind of technology so that we can reassemble the same bottle. Okay.
Then no need of recycling.
No need of recycling. Yes, only teleportation.
Only teleportation.
Yes. Okay. So, any other question? Any other? Of course, yeah. Dosh algorithm implementation we have not seen. We will see it later on in the later classes. I'll do it myself. Okay. And yeah, tomorrow we are going to cover this Grover's algorithm. If someone has taken the notes of all those things, try to understand it because those would be requiring Grover's algorithm. Slides would be given, but actually the basic phenomena, the working part,
that will be done.
that you have to do.
हमारा 10
And one more thing I want to tell you. One more thing, fun fact I want to tell you. That today we have gone through all those communication protocols, QKD protocol. We have talked a lot about BB84. Do you know where it was proposed? Very interestingly, it was proposed in Bangalore. Yes, in a conference. The first QKD protocol of quantum computing. First, that we understand that how quantum computing can be taken into the application of key distribution. First algorithm was proposed in Bangalore. So we can see India actually got all those things earlier as well. And now in the very starting of quantum computing as well, it has seen all those things. So let's bring let's take that further and try to make this happen again.
Actually, whatever we are talking about teleportation is already there in ancient ages.
Yes, of course. Supernatural.
Rishi.
Yes, of course. Even though I am in
YouTube आदमी